class, this is Dr. McGonigal with another Research Methods 2 lecture for you. Today we are going to talk about inferential statistics. So in previous videos we have covered descriptive statistics and we've covered data cleaning. So if you haven't viewed those videos yet, then I suggest that you stop this video and watch those first before you learn about inferential statistics. Inferential statistics are statistics that allow you to test your hypotheses. So in this video, we're going to review null hypothesis significance testing, and we'll talk about what types of inferential statistics you can use with what types of variables and data that you have. Be sure that you're reading Price Chapter 13, the introduction, the understanding null hypothesis testing, and some basic null hypothesis tests and additional considerations. In terms of our stages of data analysis, we've gone through Stage 1, data entry or importing our data via SPSS. Stage 2, we've learned about data cleaning and preparation for analyses. We've also covered Stage 3, which are your descriptive statistics. Now we're in Stage 4, and today we're going to talk about inferential statistics, and specifically talking about types of statistics that will allow you to test hypotheses about differences between groups in terms of their mean levels, and relationships between variables. In terms of an overview of inferential statistics, researchers study samples because we can't study entire populations. You probably remember this from your statistics class. With inferential statistics, we seek to draw conclusions, in other words, make inferences, hence the name inferential statistics, about a population using a sample. So let's go over an example of what I mean by that. If you wanted to compare mean levels of anxiety, so anxiety would be your DV or your outcome variable, for different types of therapy, and therapy is your independent variable, you may expect a difference in anxiety levels depending on the effectiveness of the therapy type. So again, you're looking at average levels of anxiety based on different types of therapy that people have received. So you expect that difference to exist. However, you want to make sure that any differences that you observe are due to actual differences in the therapy types and not random error or chance. Inferential statistics in this example give us the probability that any difference observed in anxiety levels reflects random error rather than a real difference. We set a cutoff value of how much chance we are willing to take that our results are due to random error. And that cutoff is usually p of less than 0.05. So hopefully you remember this from your statistics class, p of less than 0.05. So what does that actually mean? This is the cutoff of how much chance we're willing to take that our results are due to random error. And p of less than 0.05 means that we're willing to assume less than a 5% chance that the results are due to random error. In terms of null hypothesis testing, you need to know about the null and the alternative hypothesis for this to make sense. So let's go over the null hypothesis first. This is often termed HO, null hypothesis, or H0. This is a statement of no difference between means, no correlation between variables, etc. So it's the null. It means there's nothing there. There's no relationship. There's no differences. For example, in the full population, anxiety levels will be equal regardless of treatment type, and any observed difference is due to random chance or error and is not meaningful. You don't formally state the null hypothesis in your paper. The hypothesis that you do state in your paper is called the alternative hypothesis, or sometimes called the research hypothesis, or H1. This is your actual hypothesis for your study with directionality. So remember how you learned how to create a hypothesis and that your hypothesis has to be directional, has to say exactly what you think will happen with your variables or with your data or with your groups. For example, After treatment, participants who receive cognitive behavioral therapy will have lower anxiety scores than participants who receive psychodynamic therapy. So we are making a specific prediction based on what we know about cognitive behavioral therapy and its treatment for anxiety. So you state the alternative hypothesis in your paper as hypothesis 1, and then your hypothesis 1 and hypothesis 2, just the same way that you did for your paper 1. Remember that with null hypothesis testing, we cannot prove a hypothesis with our studies. I have been coming back to this point throughout the semester. And just a reminder to not use the language of proving a hypothesis in your papers. Instead of proving a hypothesis, remember that we either reject the null hypothesis or we fail to reject the null hypothesis. So remember, our null hypothesis is that there's no effect. We don't have the effect that we're proposing in our alternative hypothesis. So we can either reject the null, in other words, we find a statistically significant effect when there is a low probability, less than 5% probability in most cases, if our p is less than 0.05, that the observed difference in means or correlation between the variables is due to chance. We fail to reject the null hypothesis. In other words, we do not find a statistically significant effect when the probability that the observed difference in means or correlation between the variables is due to chance. So the probability is greater than 5%, again, if our p-value is less than 0.05. In this manner, statistical significance means that there is a low probability that the observed data result, for instance, your difference in means or your correlation, is due to random error. But how low? Remember, our alpha level is what we use, and typically we use p of less than 0.05. However, sometimes we might use an alpha that's lower than that, like p of less than 0.01. Or we might use a slightly higher alpha, like p is less than 0.10. It's important to remember that any decision to either reject or not reject, to fail to reject your null hypothesis, is based on probabilities rather than certainties. Because with science, we're trying to figure out what's going on, but again, we can never know. We do studies to test things, to enhance our understanding. But our decision to reject the null or to fail to reject the null, it may or may not be correct. When we are not correct, it's one of the following errors. A type 1 error is when we reject the null hypothesis when we shouldn't. In other words, we reject the null hypothesis when in fact the null hypothesis is true. There's really no mean difference or correlation between your variables, but you find that there is. So you're incorrectly rejecting the null hypothesis. In other words, you do find a statistically significant result, so your p-value is less than 0.05, even when there is no actual effect in the population. On the other hand, a type 2 error is when you fail to reject the null hypothesis when the null hypothesis is actually false. In other words, there really is a mean difference in anxiety levels based on therapy, or there is a correlation between your study variables, but you do not find one. In other words, you do not find a significant result. Your p-value is greater than 0.05. However, there really is an effect in the population. So you can see how both of these things are errors. They're just slightly different, where a type 1 error is a false rejection of the null, and a type 2 error is a failure to reject the null, and we should be rejecting the null. The probability of your errors is determined by the alpha level that you set. So choosing a lower cutoff value, for instance, choosing an alpha of less than 0.01 instead of 0.05, so a 1% chance of random error rather than a 5% chance of random error. This means you are less likely to make a type 1 error, so you're less likely to falsely reject the null hypothesis. So there's less of a chance of you finding a significant effect, but there's less chance that you're stating that an effect exists when in fact it doesn't. At the same time, a lower cutoff value or a lower alpha, like p of 0.01 rather than p of 0.05, makes it harder to find a significant effect when it does really exist. And this makes a type 2 error more likely. In other words, you're more likely to fail to reject a null hypothesis when you should be, if you are lowering your cutoff value, your alpha. So I want you to think about this for a moment. I realize that this is a complex topic and may take some time for you to wrap your head around. So I want you to think about the types of research questions in which you may want to have a lower alpha or a higher alpha. In other words, are there different situations in research in which you would want to be more certain about your decision to reject the null hypothesis? You might be more concerned about committing a type 1 error. Are there alternatively situations in which you may want to use a higher alpha? In other words, you are less concerned about a false rejection of the null, and you're more concerned about finding an effect when it really does exist. So think about that for a moment and pause the video if you need to. All right, so let me give you an example. So spoiler alert, I'll give you an example now. If you haven't paused the video and you want some time to think about it, go ahead and do it now. But we may want to use a lower alpha value. In other words, we set our cutoff value being lower to prevent us from making a type 1 error, to prevent us from falsely rejecting the null hypothesis, when the outcome is very important for people's lives. So for example, if a researcher is creating a new drug that they suspect might be helpful for cancer, and that drug has some side effects associated with it, you don't necessarily want to use a very high p-value in that case, right? You don't want to take the chance that what you're finding in your results is due to random error. You really want to be sure that it's making an impact on people's cancer. Therefore, in that case, you might want to lower your alpha value. So when we have something that we consider to be high stakes, meaning that it has strong implications for people's lives, and the results could be harmful to individuals potentially, then we want to use a lower alpha because we want to be more certain that if we are seeing an effect, it is reflective of a true effect and not random error. When should we use a higher alpha? Well, kind of the flip side of that, when our research questions are low stakes, when they don't impact people's lives as much, and we simply want to find an effect and the results will not necessarily impact people's lives negatively. Maybe we want to make a decision for an organization and we have some information and we don't necessarily think that the decision will negatively impact people's lives. In that case, we could use a higher alpha value. Let's review types of variables. We went over this in your measurement slides, so if you haven't watched the measurement lecture yet, please pause this video or stop this video and go ahead and review that. Remember from that lecture that we have two main types of variables. The first is categorical or nominal, and in this type of variable, numbers may be assigned to them, so we might assign our categories to be a 1 or a 2 or a 3, for instance. But those numbers have no inherent numerical value. In other words, higher numbers do not indicate more of something. One example of a categorical variable is gender. So we might assign male 1, female 2, transgender or non-binary or other could be a 3. We have assigned those numbers to our categories. However, those numbers do not indicate anything. 3 is not higher than 1, 2 is not higher than 1. So that's an example of a categorical or a nominal variable. A quantitative variable is when numbers have meaning. For example, on a Likert type scale, 1 might be strongly disagree, 2 might be disagree, 3 might be neither agree nor disagree, 4 might be agree, and 5 might be strongly agree. The numbers in that case do have meaning. Higher numbers mean that you more strongly agree with that variable. The types of quantitative variables that you might encounter include ordinal or interval and ratio. And again, those are all gone over in detail in your measurement slides. So having reviewed the different types of variable, let's talk about how to choose which statistical test to use, because we're going to use that information about the variable type in order to correctly select our statistics, our inferential statistics. To choose the correct inferential statistics for your study, take the following steps. Number 1, determine what your predictor variable is. Number 2, determine whether your predictor variable is categorical, nominal, or quantitative. Step 3, determine what your outcome variable is. Step 4, determine whether your outcome variable is categorical, nominal, or quantitative. And step 5, based on these answers, select the appropriate test. Some general guidelines to follow when you have 2 variables in your study. If both variables are nominal categorical, the only test that you can use in that case is called a chi-square test of independence. If they are both quantitative variables, if you have 2 variables for which numbers are inherently meaningful, you can use a correlation or a regression. And these types of statistics test relationships between variables. If you have a nominal predictor or independent variable, with 2 groups or levels in a quantitative outcome or dependent variable, then you use a t-test, and this is a test of mean differences in an outcome by group or occurrence. If you have a nominal or categorical predictor or independent variable with 3 or more groups or levels in a quantitative DV or outcome, then you use an ANOVA. And again, this is a test of a mean difference that looks for differences in an outcome variable by group or occurrence. So we're going to come back to this slide as we go forward in terms of figuring out which statistical tests to use. We'll first talk about the test for dependence, which is our chi-square test. Again, this is used for nominal or categorical data when you have both your independent and your dependent variable being nominal or categorical. And it tests whether these variables are independent or dependent or contingent upon one another. For example, if we had sales associates in 12 separate regions within the United States who worked toward the same sales goals in the last fiscal year, and we measured achievement of sales goals as 1 being yes, they achieved their sales goal, and 0 meaning that they did not achieve their sales goal, our question might be, was the achievement of the sales goal dependent upon the region that they were in? Our predictor variable is sales region, and that's nominal, right? Categorical. Our outcome variable is achieved their sales goal or not, 1 or 0, and again, that is also nominal. So we can go back to slide 11 and see that the test that we use when our predictor and our outcome variable are both nominal is the chi-square test, right? So I'm going back to slide 11. If they are both nominal variables, I'm picking a chi-square test. Okay. Just to note that you will probably not use a chi-square test for your paper because there are very few nominal variables in your data sets. Let's move on to talk about correlation. For example, I might have a hypothesis that self-efficacy will be positively related to GPA, and my variables may be measured in terms of the following. We measured self-efficacy on a scale ranging from 1, very low, to 5, very high. So in that case, numbers are meaningful. We measured GPA on a 4-point scale ranging from 0.0 to 4.0. Again, that's a numeric variable. Higher numbers mean more GPA. So let's go through these same steps that we talked about earlier to help us understand which is the appropriate test. So number 1 would be identifying the predictor. Number 2, identifying whether our predictor is nominal, categorical, or quantitative. Same for the outcome variable in 3 and 4. So let's see what that looks like. Our predictor variable in this case is self-efficacy, right? Is our predictor variable categorical, nominal, or quantitative? Well, it's quantitative, and how do I know that? Because it's measured on a scale from 1 to 5, where 5 is very high and more self-efficacy than a 1, which is very low. So we have a quantitative variable. What is our outcome variable? Well, that's GPA. GPA is measured on a 4-point scale ranging from 0 to 4. So our GPA is quantitative as well. So what type of analysis do we use when we have two quantitative variables? Well, we can go back to slide 11, and we see that if our variables are both quantitative, then we can use a correlation or regression. And we're specifically focusing on correlation for this class. Okay, so we know that we're going to use a correlation, and we want to look for a relationship between those variables. In other words, we look at a correlation value to see if a positive and statistically significant correlation exists between self-efficacy and GPA. Just a note that we could use a regression here, but again, we're not covering that in this class. In terms of a correlation, there are two things to interpret: strength and direction. Your strength of your correlation ranges from -1 to +1. Remember that the weakest correlation is 0, and the strongest correlation is either +1 or -1. And in terms of direction, you can either have a positive correlation or a negative correlation. Let's get some practice interpreting the following correlation values. So number 1, the correlation between hours spent studying and grade on exam was 0.7. Is that a positive or a negative correlation? It's positive, right? So what does that mean? That means that as hours spent studying goes up, grade on exam goes up. That makes sense, right? Now let's look at the number, 0.7, the magnitude. What is the strength of that correlation? Is it close to 0, or is it closer to 0, or is it closer to 1? Well, it's closer to 1, right? So that indicates to us that it is pretty strong. Let's look at number 2. The correlation between hours playing video games per week and final course grades was -0.56. Is that a positive or a negative correlation? It's a negative correlation, right? Does this make sense? Well, yeah, right? Because as hours playing video games goes up, final course grades goes down. Is it strong or weak? Well, is 0.56 closer to 1 or closer to 0? It's closer to 1, and in fact, it is a fairly strong correlation. Let's go through another example, and this time we'll be talking about something different than correlation. We'll be talking about mean differences. Our hypothesis is that workers who are managers experience greater job satisfaction than workers who are not managers. How did we measure our variables? We classified workers as 1, not a manager, and 2, manager. And we measured job satisfaction on a 5-point Likert type scale. So again, we need to answer these 4 questions to determine what is the appropriate statistical test. So, number 1, what is the predictor variable? Well, that is managers versus non-managers. Is this categorical, nominal, or quantitative? Well, it's categorical nominal because we have given them numbers 1 and 2, but those numbers have no meaning on their own. And we see that we have another question here, a follow-up question, as to how many levels we have of our categorical nominal variable in this case. And the answer is 2. It's 1 non-manager or 2 manager. So there are 2 levels. What is the outcome variable? Well, that is job satisfaction. Is the outcome variable categorical, nominal, or quantitative? It's quantitative, right? And how do we know? Because we have a 5-point Likert type scale. What is the correct statistical test for a nominal predictor and a quantitative outcome? Well, let's look back at slide 11 to find out. If we have a nominal predictor with 2 groups and levels, or a quantitative outcome, then we are using a t-test. And in fact, that is what we have, right? We have 2 levels within our variable, manager and non-manager. In other words, we are looking for differences in job satisfaction between managers and non-managers, such that managers have significantly higher levels of job satisfaction than non-managers. Let's talk for a moment about the importance of statistical significance testing in this case. So again, our hypothesis is that managers experience greater job satisfaction than non-managers. And so why can't we just look at the average levels? We talked about descriptive statistics in our last video. So why can't we just calculate means and look at 1 mean for managers and 1 mean for non-managers and see if the manager's mean is higher? The answer is that we also need to know if any mean differences that we see are large enough to be considered true, or if they could be due to chance. So remember, we talked about statistical significance testing, meaning that we want to be sure that our results, or we want to have some level of certainty that our results are not due to chance. So rather than simply looking at those mean levels by group, we conduct what we call an independent samples t-test, and this tells us whether the means for managers and non-managers are significantly different from one another. Let's talk about another example now. This hypothesis is that college seniors experience more stress than college sophomores and college juniors. We classified students in terms of our predictor variable as sophomores equals 1, juniors equals 2, seniors equals 3, and we measured stress on a 5-point Likert type scale. What is our predictor variable? Well, that's college status, and we have senior, sophomore, or junior. Is it categorical or quantitative? Well, it's categorical or nominal. And how many levels do we have? In this case, we have 3, right? What is the outcome variable? That's stress. And stress is a quantitative variable because it's measured on a 5-point Likert type scale. So we now need to determine what is the correct statistical test. And we can look back at slide 11. And we can see that if we have a nominal predictor like we do with seniors versus sophomores versus juniors, and we have 3 plus groups, we have 3 groups in a quantitative outcome, which is stress, then an ANOVA is the correct test for us. In other words, we look for differences in stress levels between seniors on the one hand and sophomores and juniors on the other hand, and specifically whether seniors' levels of stress are significantly higher than those of sophomores and juniors. Let's talk about another example. Here is a hypothesis for you. College seniors experience more stress at the end of their senior year than they do at the beginning of their senior year. Let's think about that for a moment. So in this case, we're not comparing one group of people to another, like seniors versus sophomores. Instead, we're comparing one time point to another, beginning of senior year versus end of senior year. And we're doing so for the same people. So in this case, we have 2 time points, beginning and end of senior year, and we have a nominal predictor, which is our beginning and end of senior year, and a quantitative outcome, which is stress. Because we have a nominal predictor and a quantitative outcome, and we have 2 levels, we do know that we want to use some form of a t-test. However, the form of t-test that we're using is slightly different than what we just went over. And instead of an independent samples t-test, in this case we're using what's called a paired samples t-test. So we're going to recap, and I'll just take a moment to let you know that we're going to go over how to conduct these tests in separate videos. So today is just about conceptually understanding null hypothesis significance testing and understanding which test to choose for which type of situation. So with that, we'll recap. If you have two groups or categories or occurrences of your predictor, then you're going to use a t-test of some sort, whether it is an independent samples t-test or a paired samples t-test. If you have three or more groups or categories or occurrences of your predictor, you're going to use an ANOVA. For testing different groups of people, you're using independent samples tests. For testing the same people over multiple occurrences, you're using repeated measures, or also known as paired samples tests. And just as a note, all of these are for numeric outcomes only, quantitative. So for instance, Likert type, interval or ratio type outcomes, and not for outcomes that are categorical. Do you remember what the type of analysis is that we can use for our categorical variables that we learned about earlier? So that's the chi-square test. This slide summarizes the various decision points that you have and how you can arrive at the correct analysis to use if your hypothesis is about a mean difference. So this is not about correlation, this is just about mean difference. So ask yourself, how many levels does your predictor have? If it's 2, then you can ask yourself, is it the same participants or subjects or different subjects? If it's the same, then you use a paired samples t-test. If it's different, then you use an independent samples t-test. If you have more than 2 levels of your predictor, then you're using an ANOVA. So one more summary for you. T-tests and ANOVAs provide ways to compare groups of individuals on the basis of an outcome variable, so a DV or an outcome variable, OV. T-tests are used when you have 2 groups or occurrences of a dependent or outcome variable. For example, do men and women differ in their grades, their levels of grade satisfaction? Another example is, do all students' levels of grade satisfaction decrease from the start to the end of the semester? So in both cases, you could have a t-test. Our ANOVAs are used when you have more than 2 groups. So for example, do freshmen, sophomores, juniors, and seniors differ in their levels of grade satisfaction? Do students' levels of grade satisfaction differ from the beginning of the semester to the middle of the semester to the end of the semester? So in the first case, you have freshmen, sophomores, juniors, and seniors. You have 4 levels of your variable, your predictor. So that means you have more than 2, which means you're using an ANOVA. In the second one, you have time points, beginning, middle, and end. So you have 3. And so that also indicates that you would be using an ANOVA. So let's take some time now for you to check your understanding of what we've just gone over and apply it to select the appropriate statistical test for each of the following. So go ahead and complete this and check on the next slide when you're done. And no peeking. So check to see if you have an understanding of these types of tests. And after you're done, that is the conclusion of this video for today.